Question number 14, what does it say? Electrostatics, a little bit of vectorial computation will be required. There is a cube of side A and that has a point charge Q each at all the vertices except the one which is at the origin where the charge is minus Q. We got to calculate the electric field at the center of the cube. Now, a little bit of thought process is involved, and let's see, because the first thing we need to do in objective question is we got to look at the option so that we can modify and tailor-make our answer according to the option. So clearly, the k has to be replaced by 1 by 4 pi epsilon naught, ijk that has been represented by x cap, y cap, z cap, that hardly matters. So it has to be written in a vectorial way. Now, is it that we'll start writing the field due to each and add them vectorially? Well, in principle, yes, but we are not going to do that. Because see, if you just try to see that this minus q, if I split as q and minus 2q, that's what I need to do. Now, you could see here the total charge would be minus q. And by doing so, you know, the electric field due to all q at the center would be 0. So when I say all q, even you got to involve this. So all those 8 charges of q each at the vertices, the electric field at the center will be 0. How come? By symmetry. So I just need to calculate only and only the electric field due to minus 2q. And that too vectorially. So now you know the expression is that kq r vector divided by r cube, where this q is sign sensitive, right? So how do you do that? First of all, k, which is 1 by 4 pi epsilon naught, q is minus 2q, and what is r vector? The vector joining the origin to the required point, the center of the cube. So what would be the r vector? That's going to be a by 2 x cap plus a by 2 y cap plus a by 2 z cap. That's what we do, isn't it? The x cap, y cap and z cap, they are correspondingly the I cap, j cap and k cap. That's not a big deal, all right? So that has been written. Now, one more thing is remaining. At the denominator, we got to go with r cube. So how much will that be? That's going to be first the magnitude cube. You got to be careful with that. So how much is the magnitude? Root 3a by 2 and cube. So this is all. Now a little bit of plus and minus and calculation that you need to do. I don't think so there will be any trouble in doing so. So when you do that, your answer is going to match with option number 4, all right? So you need to replace k as 1 by 4 pi epsilon naught. So guys, that was about question number 14. Let's move to question number 15. Question number 15, all right, gravitation, but the previous gravitation was extremely simple. This one requires a little bit of thought process. 4 identical particles of masses 1 kg, they move along the circumference of a circle of radius 1 meter. Now, if these particles are moving in circle, there must be an agent which provides the centripetal force. And that agent provider is the net gravitational force. So we'll see the symmetry of the situation says that net gravitational force will be acted towards the center, and that will itself act as the centripetal force, all right? So now let's see. We got to calculate the speed of each particle, all right? A little bit of calculation is required, but no problem. We're not going to worry on that. So here, you know, these are the 4 vertices, and then we also need to make a circle. So let me come up with this idea, all right? So to make the circle here, all right, now let's see, a little bit of adjustment would be required. Perfect. Okay. So here is that circle what I have made, and then the particles are moving along this. So this much is fine. A little bit of, mismatch, you just neglect it. There's no point being so much of precise. All those particles are here. Like this is the 1 kg particle. This is the 1 kg one. This is the 1 kg one. And even this, that's a 1 kg one. And it says that the radius is 1 meter. You get that point? Now, if I say A and A are the sides of the square, that would be same. Let's just try to relate, all right? Let us relate this A in terms of the radius. Now, you know that this is the diameter, isn't it? So what would I get? The first thing is that root 2 times A is the diameter, and that will be equals to 2 meter. That's the first thing, because the diameter would be 2. So I get the value of A, that is under root of 2. Perfect. Now let's just consider one particle. You need to consider any one. So any one experimental, that's perfectly fine. Now let us see what is the direction of the force. Like this 1 kg will attract it here. This 1 kg will attract it here. This 1 kg will attract it here. And you could see, if I call this as F, this as F, this as F dash, the resultant of F and F each will come along this. That would be added with F dash. So let's see. All right, the first thing is that how much is F? That is G m1 m2 divided by r square. That's a force between neighboring 1 kg particles. And what is F dash? F dash is G m1 m2 divided by the diameter square, right? And how much is the diameter? That is 2. So we've calculated F and F dash. How much is the resultant force? The resultant force is root 2F plus of F dash. Root 2F will come here plus of F dash, and that is equals to mv square by r. Now the value of m, that you need to substitute as 1 kg. You get that point? We calculated the net force and we equated it to mv square by r. And guys, when you do that, you would get option number 1 as the correct one. All right, so that was a bit of calculation involved. Question number 15. Now it's time we move to 16th question. What does question number 16 say? A little bit of idea about simple harmonic motion. In the given figure, a mass capital M is attached to a horizontal spring. So here it is, the capital M, the spring. That has been said by the first statement. The spring constant of the spring is K, cool. So here K is given there. And only that capital M oscillates on a frictionless surface with a time period capital T. So when there is only the larger block, that larger block will oscillate with a time period of capital T. You get that point? And of course the amplitude is capital A as well. Now when that mass is in equilibrium during the course of oscillation, when it passes the equilibrium position, another mass small m is gently fixed upon it, very gently, all right? Now we got to calculate the new amplitude. Now if you see here, where is that little mass added? At the mean position. Now see, at the mean position, the net force is already 0, because that's the definition of the mean position. And on top of that, the little mass is added very gently. That means the entire procedure is conducted under an environment of net force 0. And if net force is 0, what happens? The linear momentum is conserved, right? So let's see. How much is the initial momentum? Capital M and the velocity. And how much is the velocity? Don't forget, it's at the mean position. So omega times A. And how much is omega? Root of k by capital M. The amplitude is A. That's how it comes. All right, then how much the final? That will be m plus small m is the new mass, and k by m plus small m. Don't forget, the spring constant is same, but the new angular frequency is going to be this much, and the amplitude is A dash. That's all done. So if you solve this, if we try to match it with the option number 3 comes out to be the correct one. Let's go to the next one.